Good afternoon, everyone. My name is Sean, and today I'll present on my undergrad thesis on symmetries in particle physics. So firstly, let me just give a brief introduction. Let me just mention schematically what Noether's first theorem says. So Noether's first theorem, in words, says that if an action integral is invariant under a finite dimensional continuous group of transformations, then there exists a conserved quantity for each independent symmetry. Or schematically speaking, a symmetry in a system implies a conserved quantity. And in my presentation, I want to go through a mathematical framework that allows us to study symmetries and these conserved quantities in particle physics. So the goals for this presentation comes in two parts. The first part would be to talk about classical mechanics and develop a nice framework that allows us to extend to the second part, which is on classical field theories. You can see here that for the first part and the second part, we have pretty much the same kind of format, where I will introduce the Lagrangian formalism for classical mechanics and field theories, and then we'll talk about two types of symmetries for each of the two cases. So let's begin with classical mechanics. And for this part, I will go slightly faster because I think this is quite well established in physics literature. So firstly, let's just recall what a Lagrangian is. The Lagrangian is basically just kinetic energy minus potential energy of a physical system. The problem here is that for Noether's theorem, we want to study the invariance of an action functional, right? So we need to consider a path through which a particle traverses. And our first job is to denote or figure out a way to denote such a path, which is, I think, some basic calculus. So we want to parameterize. I think the display got disconnected. Let me just share again. I think my window crashed or something. Sorry, let me just So let me continue from here. Yeah, so from basic calculus or multivariable calculus, we know how to parameterize a curve. So in our case, we want to parameterize a curve using some interval of real numbers or some interval of time. And the curve will live in some configuration space. For simplicity's sake, let's consider, for example, R3. We can also define the velocity that we require for the Lagrangian by simply finding or computing the directional derivative along the curve. So this leads us to kind of like a different way to talk about the Lagrangian, and in this case it will be a Lagrangian but evaluated on a curve. And this is nicely identified with the Lagrangian that we know from physics. So there's nothing much that's different here, simply that we can now define the action functional like such. So the associated action functional of a Lagrangian is the map from the space of smooth curves parameterized by some interval of time, and what it does is assign a real number to every path. So I included a remark here at the bottom that says that by extremizing the action functional, we can obtain the classical path of a particle, which is what we know as Hamilton's principle of stationary action. And this path is the solution to Euler-Lagrange equations. So now that we have the action functional defined, we can start talking about symmetries. Symmetries in classical mechanics. So schematically speaking, schematically speaking, the symmetries in classical mechanical systems can be summarized using this diagram. So as previously discussed, we parameterize a curve using this Q that maps from some interval in real numbers to the configurational space. And symmetries can act on the left side, which is on the parameter space, as well as on the configuration space. So I have a few motivating questions for the next few slides. One thing is, first question is, what can the groups be? Second question is, how do we check if the action of the system is invariant under some transformation? Or basically, how do we check if a Lagrangian is a symmetry? How do we check for symmetries? And the last question is, what does the Noether's theorem tell us about the conserved quantity? So, firstly, let's talk about configurational symmetries, which is quite well established in the literature. So I will not dive into too much of the details. So firstly, let's define what a Lie group action on the configuration variable. What is a Lie group action on the configuration variable? So I think this is quite covered in quite a lot of textbooks, standard text. So I'll just briefly mention that a Lie group action on some variable basically just means that if I take an element from a group and I take some variable from the vector space or the configuration space, it should give me something else in the configuration space. So similarly at the bottom, this is how we define or how we compute the associated group action on the velocity variable. So now I introduce a condition for us to check whether a Lagrangian is invariant under some configurational transformation. So given a Lagrangian and given some group action, this Lagrangian or the Lagrangian is G invariant if it satisfies this condition, this equality here. I highlight in red the two things that we need to check in order to know whether a Lagrangian is invariant under some configuration transformation. So I give a simple example. Let's say we consider spatial translations. We can easily compute the Lie group action on the configuration variable and the velocity, and we have this condition here by simply plugging into the equation here on the previous slide, and it says that a Lagrangian is invariant under spatial translations if we get this condition fulfilled. Then we can go on to say that Noether's theorem, suppose we have a Lagrangian that is G invariant, and suppose we have a solution to the Euler-Lagrange equations. Basically, that means that if we have a classical path that satisfies Hamilton's principle of stationary action, then for all tangent vectors C to a continuous symmetry, we have this conservation law. So our job is basically, in that previous example, we want to compute C dot Q, which is the vector field where the infinitesimal generator of a Lie group action for each configuration variable that assigns a vector to each configuration variable for each Q. So by simply computing, first of all, the tangent vector at the identity, and then computing the infinitesimal generator of a Lie group action, we can plug it into Noether's theorem and derive, in this case, conservation of linear momentum. So I won't go into the steps here, but the framework that we have just gone through is going to apply to other symmetries as well as other symmetries like temporal symmetries, which I'll go through next, as well as for field theories later on. So let's dive into temporal symmetries. Similarly, we have to define the Lie group action on a time parameter, but there's nothing much that's different here. It looks basically the same, just acting on different sets, different spaces. So we see here the condition for a Lagrangian to be invariant under some temporal symmetry, some temporal transformation. Similarly, we want to check for these things highlighted in red. So I need to compute theta k, theta sub k of t and theta dot as well, in order to check whether a Lagrangian is k invariant. I give two examples. First, a simple example for temporal translations. It's quite easy to compute theta and theta dot, and by substituting theta and theta dot into this condition here, we can see that a Lagrangian would be invariant under temporal translations if this equation in equation 29 is satisfied. So this is quite well established in the literature, although they don't exactly use, I think, a pretty nice framework, if I can say so. But this framework allows us to study some slightly, I guess, weirder transformations, like this next one, which is the diffeomorphism of the parameter space. So consider some monotonic function that, essentially, intuitively speaking, it squishes or stretches the real line or the parameter space, and we use that interval, that transformed interval of time, to parameterize the curve. Then we can compute theta sub k and theta dot sub k, and substitute into the same k invariance condition to see that a Lagrangian is invariant under temporal reparametrization if it satisfies equation 31. Okay. So with these two examples, let's go through Noether's theorem for temporal symmetries. So same thing, if I have a Lagrangian that is invariant under some temporal transformation, and suppose I have a classical path, right, a solution to the Euler-Lagrange equations, then Noether's theorem says that we can derive the conservation law in equation 33, and all we need to know what is conserved is to compute this thing highlighted in red. So for time translation, we can, again, it's the same procedure. We compute the tangent vector at the identity, and we compute the infinitesimal generator of the Lie group action on the time parameter, and then we plug it into Noether's theorem and see that we get the law of conservation of total energy in this case. This is well established in physics literature as well, but what is not so commonly seen in the current literature is the Noether's theorem for time reparametrization invariance. So again, it's the same framework. I compute the tangent vector at the identity, I compute the infinitesimal generator of the Lie group action, and then we plug it into Noether's theorem, and the weird thing is that we get this condition that the total energy or the Hamiltonian is equal to 0. This is known as the Hamiltonian constraint. I think the Hamiltonian constraint is seen in the Hamiltonian formulation of general relativity, and the inspiration for checking time reparametrization invariance comes from string theory texts. Yep. So with this, we have talked about two types of symmetries in classical mechanics, configurational and temporal symmetries. Now we can move on to classical field theories and discuss how to check for symmetries and conserved quantities using the same or similar framework. So firstly, let's talk about the Lagrangian formalism for classical field theory. One slight difference from the get-go is that we have to define a field. A field is, simply put, if I take any point in spacetime, and in this case we are talking about flat spacetime or Minkowski spacetime, which I denote as x, we assign some mathematical object to each spacetime coordinate or each spacetime position. We can assign, let's say, a scalar, a vector, a spinor, or even a tensor. But for the purposes of this presentation, let's limit the discussion to scalars, so we can go through some simple examples. We also need to define the Lagrangian, right? But in this case, instead of a Lagrangian, we first have to define the Lagrangian density. If we kind of spin our eyes and think about what Lagrangian is, Lagrangian is, it says something about the energy content of some particle, some physical system. Not exactly the total energy, that's the Hamiltonian, but a Lagrangian is something to do with energy. When we talk about field, right, a field is defined over all space or all space-time. So we can't actually like point at a field and say what's your energy content. So we have this idea of a Lagrangian density instead. Lagrangian density is a map that takes in three things. First, the space-time coordinate, the field at that coordinate, and the derivative of the field at that coordinate. And to get the Lagrangian from the Lagrangian density, because remember our end goal is to define the action functional, which we have to integrate the Lagrangian. So to get the Lagrangian from a Lagrangian density, I simply integrate the Lagrangian density over all of space, just like how density and mass works. Next, we kind of need some notion of a path in configuration space. But in this case, the so-called path is actually just a field. So similarly, we kind of parameterize the so-called path using the parameters, using a set of points from the parameter space. But in this case, we take some subset of the Minkowski space-time and we parameterize the field that way. So with all that, we can define the action functional. The action functional again is the map from the space of smooth, in this case, smooth curves in space-time, and we assign each field a real number. So I put down a remark at the bottom again, similar to the case for classical mechanics, that if we extremize the action functional, we can obtain a classical field that solves the Euler-Lagrange equations, but in this case, the field theoretic Euler-Lagrange equations. So now, well, previously we talked about, or I showed the kind of the roadmap for studying symmetries in classical mechanics. For classical field theories, this is a lot more complicated. Just to point to the parameter space, the parameter space is the Minkowski space-time somewhere in the middle here. What we can do is we can define different fields on space-time. We can define, let's say, some scalar field, in this case a complex Klein field. We can define, let's say, vector fields like these two. So vector fields that take real valued vector fields and complex valued. We can also have spinors in this case. For this presentation, I'll mainly talk about the simpler cases. So we will talk about symmetries that act on the complex scalar field and the symmetries that act on space-time itself. So let's give two motivating questions. First, how do we check if the action of a system is invariant under some transformation? Basically, how do we know if Lagrangian has a symmetry? And next, what does Noether's theorem tell us about the conserved quantity? So first, let's talk about internal symmetries, or well, configurational symmetries. Again, I flashed the definition of a Lie group action, but it's very similar to the previous cases. So I will skip this slide. So let's introduce the condition for a Lagrangian to be invariant under some group action. Given a Lagrangian density and given a group action, a group, we need to check for two things. First thing is the group action, the Lie group action, on the field variable, as well as the velocity analog, or how the Lie group action on the velocity variable, or the derivative of the field variable. I give one example. So suppose I want to check for U1 symmetry for the complex Klein volume field. I need to compute two things, which are the two red things here: the Lie group action on the field variable and the Lie group action on the derivative. So I compute these two things for the field variable, as well as the complex conjugate for the field variable. And when I plug it into the condition on for G invariant Lagrangian, we see that the complex Klein Gordon field is invariant under U1 transformations. Now, Noether's theorem for internal symmetries, quite similar to classical mechanical case. We suppose we have a Lagrangian density that is G invariant under the group action, and let us have a solution to the Euler-Lagrange equations. Then for all tangent vectors C to a continuous symmetry, we have this conservation law. In order to derive what the conserved quantity is, we simply need to compute C dot phi, which is the infinitesimal Lie group, infinitesimal generator of Lie group action on the field variable. So we, again, if you recall from the classical mechanical case, we compute the tangent vector and the identity, we compute the infinitesimal generator, and then we plug it into Noether's theorem to obtain this equation here, which says, which tells us the global conservation of U1 charge, or I guess in physics, we typically say that this is an electric charge. So now we come to, I think, the biggest part of this presentation, which is space-time symmetries. So again, Lie group action on space-time, in this case, space-time coordinates, but it looks pretty much the same as for temporal or time coordinates. Okay, so here I introduce K invariant Lagrangian. So suppose I have a Lagrangian density and I have a group action on space-time coordinates. This Lagrangian is K invariant if it satisfies this equation here, or this condition here. So in order to check if the Lagrangian is invariant under some temporal or spatial temporal transformation, I need to check the Lie group action on the space-time coordinate, as well as the Lie group action on the derivative of the field. But one thing to take note here is that I have this extra factor outside of the Lagrangian density. So in the derivation of this condition here, what we did was to impose the fact that the action must be invariant. So when we do a space-time transformation, what we're actually doing is just doing a change of variables in the integral for the action functional. So this is simply the Jacobian. So we need to compute these three red things to check if the Lagrangian is invariant under some space-time transformation. So again, we will go through the simplest example, but it's quite tough. So let's take the Klein-Gordon Lagrangian density again, and I compute the Lie group action on the space-time variable, space-time coordinate. I compute this, which gives us this thing here, because I just want to find how the Lie group action on the space-time coordinate transforms the field derivative. So I compute that as well. I compute the Jacobian, and we plug everything here into the condition for K invariance. So we see that after a bit of working, and I skipped quite a bunch of steps here, but eventually we get that an important condition is that the determinant of lambda here must be 1, because the Jacobian, if the Jacobian is not 1, then the action is not invariant. In this case, this tells us that the Lagrangian density, the Klein-Gordon Lagrangian density is only invariant under proper Lorentz transformations. proper as in when the determinant is 1. So we have to restrict ourselves to the special orthogonal tree 1 group. So now that we have a symmetry, we can define or we can show Noether's theorem and Noether's theorem for space-time symmetries. And it says that suppose I have a Lagrangian density that is invariant under some space-time transformations, and suppose I have a solution to the Euler-Lagrange equations. Then for all tangent vectors to a continuous symmetry, we have this conservation law. It looks a lot more complicated than the previous examples, but a summary of this, or how to use this, is that we need to compute this thing here. The notation here is using Einstein's summation convention, so it is written in like coordinate form. But what this red thing here that I highlighted is that this is a vector field that assigns to each space-time coordinate a infinitesimal generator of space-time transformations. So we need to compute that, and following the same exact framework, we compute the tangent vector at the identity, and then we compute the infinitesimal generator of the Lie group action on space-time coordinates. And by plugging this into this version of Noether's theorem, we obtain this conservation law here, where m mu gamma lambda is the angular momentum tensor, and that's the conserved quantity in this case. With that, I come to the end of what I want to present, and maybe I'll just give like four possible future directions for this project. The first two would be to then, if I can go back to this diagram, the next step would be to look at local gauge symmetries for vector fields like this, which describe electromagnetism and weak and strong force. The next one, and I think I would say the hardest one, would be to check for symmetries in spinor fields. And one difficulty here would be that the space-time symmetries act not just on space-time, but as on the spinors, on the spinor fields themselves. And last 2 points here would not be covered in my project, but we can extend this to mechanical systems on manifolds and field theories defined on curved spacetime. And that's the end of my presentation. Thank you.
So first question is, do you have any original contributions in your project?
Yeah, so I think one of the biggest contributions that my project has to offer is having a nice framework for us to study symmetries, especially on the parameter space. So for classical mechanics, it would be how to study temporal transformations, temporal symmetries, and for the field theory case, it would be to study space-time transformations. I think this is not very well done in the current literature, so I hope I did a good job introducing the framework that we can use to study these types of symmetries.
Okay, next question about the Lie group action you mentioned a few times. Can you go back to one of those slides? So I was just wondering, why do you specify Lie group here? It looks like it could be any group following this definition.
For Noether's theorem, we can only consider continuous symmetries, and from what I understand, that's described by Lie groups. So it can't really be, for example, let's say time inversion or parity transformations, because those are discrete symmetries. And yeah, that's the reason why Lie group action has to be defined.
Okay, can you go back to slide 14?
Yeah.
Yeah, on this slide you have some bold G and some non-bold G. So is there significance of making the G bold?
Oh, sorry. I think it's because I copied codes from my LaTeX code from different places. Okay, because personally, I usually use both font for vectors in R3, but I guess in general, I don't think it really matters whether I hold it or not. So I think it's, to answer your question, it's mostly typo. Yeah.
Okay. Alright, I think I have to stop there because of the time, so thanks for that, and we'll stop there, so thanks again for your presentation.
Okay, thank you.
I can ask questions too.
Yeah, you can ask.
Yeah, sure, okay.
I remember, right? So you never said these critical fields, they have to be minimum or maximum? For the actual functional, is this required or not?
You mean for the Hamilton's principle?
Yeah, they have to be minimal, maximal, or it's irrelevant for us? Or just extreme?
It should be. The Hamilton's principle of stationary action says that the action must be extremized. From what I remember, it typically is minimized, but I don't think the principle states specifically whether it's maximized or minimized. I think it's extremized.
Yeah. In 9, A is defined on some space of curves, right?
Yeah.
But when you apply it, you don't take arbitrary curves. When you apply Hamilton's principle, they have to fulfill some conditions.
The endpoints,
Right.
fixed endpoints.
Yeah, that's important or not?
As
To
in
find the
whether we
order
have
of
a
equations. Yeah. Whether they are fixed or not, to find the correct equations. Is it important?
Yeah, it is.
Yeah, it's crucial.
Yeah, we
So
have
in
to
fact,
have fixed.
none is defined on curves fixed at the endpoint. Not on all possible curves. The action function.
Yeah, but doesn't this tell us that fixed endpoints?
No, it's just for some interval to be right. Yeah.
Oh, okay.
So then some intuition, when we go to spinor, if you show our diagram, the fact that these two symmetries, they talk to each other, right? What effect this has on the conservation law? You can show the NTU conservation law. Yeah. The next, this next one. What do you guess would change here for spinors? Instead of just angular momentum, what would we have?
It's the total orbital yeah.
Plus
spin.
Yeah, we would get the total orbital spin angular momentum.
Yeah. Okay.
For me, that's it.
Dr. Greaves, do you have other questions?
No, that's all from me. Thanks again.
Thank you.